So the next topic we're going to learn about is the cross product. So why the cross product? We're still on the same track. Our goal is still, we're going to have, for a point, I'm going to have a tangent plane, and I want to figure out what is, bad color. I want to figure out what is a normal vector perpendicular to this plane. Now I know how to compute angles. So if you give me a vector, I can probably figure out using the dot product some other vector is perpendicular to it. But if I have a plane, then what do I have to do? What we're going to do is, well, if I have a plane, I can come up with 3 points on the plane and then do vectors that are parallel to the plane. And given 2 vectors, I want a third vector that is perpendicular to those 2 vectors. And that is exactly what the cross product is going to do for us. So again, I'm going to have for any 2 vectors in space, I want, for any 2 vectors, I want a third vector that is perpendicular to both. Okay? So that is going to be perpendicular to this vector and is going to be perpendicular to that vector. That vector is going to be what the cross product does for us. Okay? All right, so let's see how it works. By the way, there could be another vector in the opposite direction, right? But the cross product is very picky about the direction it takes. And you can see, like physicists and engineers, they're all the time doing these like trick with their hand about trying to figure out what direction some force is going to act. Is it going to be up? Is it going to be down? We'll figure out that the cross product is actually going to tell us is going to have one particular direction, one choice. So again, given 2 vectors, we're going to find a perpendicular one. How so? We have the dot product to help us. So suppose I have 2 vectors. For example, let's just give it names. We're going to do it like I had before. Let's say 1, 1, 0. And I have another one. Let's say the vector square root of 3 over 2, or square root of 3 over 2, 1. And now I want a different vector is perpendicular to these 2. So what is going to be my vector C is going to have some components. And if it is perpendicular to A and B, in particular, it's perpendicular to A, so it has to satisfy that A times C is 0, where this is a big dot. That's the dot product. And it has to satisfy that B times C is 0. And that is going to give me 2 equations. It's going to give me a system of 2 equations, which is A times C, that is C1 plus C2 equals 0. And B times C is going to be the square root of 3 over 2 C1 plus the square root of 3 over 2 C2 plus C3 equals 0. I have 2 variables. I have 3 variables. I have 2 equations. I can solve for one variable, put it in the other equation, and figure out what the solution system is in here. There are going to be infinitely many solutions, because if you look at the picture, any vector in this direction is going to be a solution. So there are infinitely many solutions. So I was expecting there would be infinitely many solutions. It's going to give me one that you'll see is a very special length and very special direction. That's what's going to, the cross product going to give me. But in any case, that solving systems like this is a problem for, there are 2 people here that are in my linear algebra class. I remember Reese is like Reese somewhere here. So anyway, that is what we do in linear algebra, is solve systems of this sort. This is a linear system, and we can try to figure out what the solutions for those are, but I'm not going to do that here. I'm just going to tell you what the solution is. It turns out that the cross product is defined by this formula right here. So the cross product of two vectors is going to be given by this formula that nobody remembers. You don't have to remember this formula because I don't remember it, and we come up with it in another way that has some more of a mnemonic way of doing it. For that, I have to remind you, if you haven't learned what is a determinant, because the formula that we're going to have is actually going to be given in terms of a determinant. So first of all, what is a determinant of a 2 by 2 matrix? So a 2 by 2 matrix, first of all, let me give you a matrix, is an array. A 2 by 2 matrix is an array with 4 numbers, a 2 by 2 array. And then the determinant, you calculate the determinant multiplying the diagonals and subtracting. So it's A times D minus B times C. Those are regular dots. Oh, okay, product of numbers. That's the determinant of a 2 by 2 matrix. Now, I can do determinants of 3 by 3 matrices also. So what is going to be the determinant of, let's call it A, B, C, D, E, F. So what if I want to do the determinant of this matrix? There are many ways of computing this determinant. There's several ways of doing so, but the way that I'm going to teach you, you just have to do 3 2 by 2 determinants. So it is A, so it is going to be A, and then you eliminate that row and column, and that's going to give you 4 numbers that are already in one array, and that's going to be a matrix, and I'm going to take the determinant of that matrix. Okay, so this leaves E, F, H, I. Now it is alternating, so now I'm going to do minus B times, and if you eliminate this row and column, then I'm left with D, F, G, and I, and I'm going to do the determinant of D, F, G, and I. And then C times, eliminate this row and column, and compute the determinant that is left over here. So that is D, E, G, H. So that's how you compute determinants, and we'll do a few examples in a moment. But what I want to show you is that the formula for the cross product of two vectors is given by this determinant, where the I, J, and K represent the standard basis vectors. So those are variables, or like these are just fixed letters because those are the standard basis vectors. And this row is the first vector I want to compute a perpendicular of, and then the second row is the second vector I want to compute something perpendicular to. Okay? So let's do it. Let's find the cross product of 1, 1, 0 and 0, 1, 0. First of all, do I need something fancy like the cross product to compute a perpendicular vector to these two? Or can you give me one from the top of your head? 0, 0, 1 is perpendicular. I can tell he's right because if I draw those two vectors, where are these vectors? 1, 1, 0 is here, and you can see it's on the xy plane. 0, 1, 0 is here, and that is on the xy plane. So those two vectors are flat. So if I take any vector that is perpendicular to the xy plane, that will be perpendicular to both. So 0, 0, 1 works as a vector that is perpendicular. The cross product, as I said, the length of the vector itself is going to have some meaning. So we want to compute the actual cross product to see if it's going up, if it's going down, and what is the actual length, because I'll tell you in a moment what the meaning of the length is. So we're going to find the cross product by computing the determinant of I, J, K, 1, 1, 0, 0, 1, 0. and we do the expansion of the determinant. That is going to be I times the determinant of 1, 0, 0. Whoop. This is the determinant that is left when I cancel the first row, first column, minus j times 1, 0, 0, 0, plus k, let me put it here, of 1, 1, 0, 1. Okay? What is the first determinant is, remember, is this diagonal minus this diagonal. So it is 1 times 0 minus 1 times 0 minus j times 1 times 0 minus 0 times 0 plus k times 1 times 1, finally something will survive, minus 1 times 0. So see, this is all 0. This is 0. So the only thing that survives is k times 1. So it is actually just the vector k. So you were right. So it is, in fact, the cross product of, if this is u and this is v, the cross product is that vector over there, and it's the unit length vector in the z direction. Let's find the cross product of two other vectors. Now these are somewhere in space. I can't tell what a perpendicular direction to this one, these two would be. So we do again cross product. Let me write it that this is going to be u, this is going to be v. The cross product is going to be ijk 1, 1, 1, 1, 0, minus 1. And it will be I times 1, 1, 0, minus 1 minus j times 1, 1, 1, minus 1 plus k times 1, 1, 1, 0. That is I times 1 times minus 1. Let me just indicate it here. Minus 1 minus 0, so this is a minus 1. Minus j times, clean that up. 1 times minus 1 minus 1. Minus 1 is minus 2 plus k times 0 minus 1. So this should be minus I plus 2j minus k. So it is actually the vector, if you want it in coordinates, is minus 1, 2, minus 1. So I did this determinant is plus k times 1 times 0 minus 1 times 1. Oh. Right? This determinant right here is 1 times 0 minus 1 times 1. So it's the main diagonal minus the product of the anti-diagonal. So if I'm going to multiply the first term will be I times the determinant that appears when I remove the first and first column. Then the second one will be when I remove, let me clear that up. If I remove this one and that one, then what is left is A1, A3, B1, B3. And then with the K, I get A1, A2, B1, B2. Make sense? Okay. Now, some of the properties that are useful for the cross product is that, first of all, it comes with a specific direction. So if you put your fingers so that this middle finger and the thumb are A and B, then your index finger points in the direction of the cross product. Okay, if you sweep from A to B, then the index finger points in the direction of the cross product. Okay, that is called the right-hand rule. And more importantly, the cross product has a very interesting length. The cross product is the length of A the length of the cross product is the length of A times the length of B times the sine of the angle between them. And why is that interesting? Because there is a geometric interpretation, which is the following. If I have an angle between A and B, the angle is theta. Then if I draw a parallelogram, a completed parallelogram between A and B, by trigonometry, this height is the length of B times the sine of theta. Therefore, the area of the parallelogram will be the length of the base, A, times the length of the height, which is the length of B times the sine of theta. So the length of the cross product is the area of the parallelogram formed by A and B, which is something neat. And it just gives you a sense of how big A and B are, and A cross B is somewhat proportional, but it just gives you a sense of what is the area that they span in their parallelogram. Okay, so now we're ready for our goal, which was find a perpendicular vector to a plane. And then next, in the next section, we'll figure out how to write equations of planes given this information. But suppose I have the following. So I have a plane that passes through 1, 0, 0, which is here, 0, 1, 0, which is here, and 0, 0, 1, which is here. If you draw the triangle, then it gives you an idea of what plane we're talking about. And then I want a vector that is going to be perpendicular to that plane. And for that, what I'm going to do is I'm going to compute two different vectors that are parallel to the plane. So I have here 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I'm going to compute this vector, the vector from here to here. Let me give that a different color. I'm going to compute this vector. Then I'm going to compute this vector, and then a vector that is perpendicular to those two vectors. Okay? So this is going to be my A, this is going to be my B, and then this is going to be my cross product of A and B, so I get something that is perpendicular. Does that make sense? So first of all, what is A going to be? A is going to be the difference between going to 0, 1, 0 minus starting from 1, 0, 0. Okay? So that is going to be the vector, that is minus 1, 1, 0. Does that look right for my vector? Is it in the same direction? It is literally a vector that goes in the back. It goes back 1, up 1. So it is that vector, which is exactly the vector A, but just a translation of the vector A. So that is correct. Now, what is B? It goes to 0, 0, 1, starting from 1, 0, 0. So the coordinates for that one will be minus 1, 0, 1. And now I'm going to compute the cross product of A and B. So it's ijk, and then minus 1, 1, 0, and minus 1, 0, 1. That is going to be I times 1, 0, 0, 1. That's called the identity matrix, by the way. J times minus 1, 0, minus 1, 1, plus k times minus 1, 1, minus 1, 0. That is, that first determinant is 1, so this is I. This is minus 1 plus 0, times minus j, that is j. And then k is minus 1 times 0, so 0 minus minus 1 is plus 1. It's k. So the vector, the cross product, is actually the vector 1, 1, 1, which if you see the symmetry of the problem, it makes sense that is exactly that vector that is just pointing straight sort of in the main diagonal of the first octant or of 3D space. Okay, so that is the solution to the problem, is that a vector that is perpendicular to that plane is a vector 1, 1, 1. So I'm trying to compute this vector here, A. So I want to go from, I want to have the direction that goes from here to here. So let me answer that right here. I have the points here and here. This is the x-axis now, and this is the y-axis now. This is where 1, 0, 0 is, and this is the point 0, 1, 0, right? So if I tell you this vector, that is the vector 1, 0, 0, and this is the vector 0, 1, 0, and the one I want is here. So what vector is that? That is actually, if I write here, this was, if this is u and this is v, this is minus u, and the diagonal here, that is minus u plus v, right? Or v plus u. So the one I want, this one, is v minus u. V was given by 0, 1, 0, and u was given by 1, 0, 0. So that's why I subtracted that way to find the vector A. That was the one that I was looking for here. So if you look at the two-dimensional perspective here, then that is the vector I was looking for, is right here. So this is the vector A from the other slide. Okay? All right. Well, thank you. We're going to stop there for today. I'll see you Tuesday.